So the first thing is on the um, on the problems that are called, it's one of the first law problem sets. I think maybe it's the differential form of the first law. They're number 4 on it. We've been kicking the can down the road for a while. So here's the deal with that. Um, so differential form of the first law, number 4. I copied it out of the book and I copied it wrong, is the answer. So it says there's, I believe it said 1 kilogram of a refrigerant um, in a closed tank. Um, it starts out with a pressure of 0.9 megapascals and a specific internal energy of 232.92 kilojoules per kilogram. And its later state has a pressure of 1.2 megapascals and a specific internal energy of 276.67 kilojoules per kilogram. Here's the stuff I messed up in copying this down. There's work done by a paddle wheel at a rate of so work is it's done on the refrigerant, so it's negative 0.1, and I guess this would be since it's a rate, that would have to be kilowatts per, well, I guess just kilowatts. And the function of time was actually the heat that dissipated from the refrigerant to the surroundings. So Q dot, that's also negative then, is equal to this constant K over 60. So I can put everything in seconds times T. So now T is in seconds. It gave it in minutes. There are times when you can leave some stuff in seconds and some stuff in minutes. It takes a lot of careful thinking about what you're integrating with respect to and whatever. There are times that it can work, but it always works to just get everything into the same units of time. So that's what I did here. So time is equal, time is in seconds. And then the questions are, what are Q and W? And what's that constant K? So the way it's written down is that the rate of work that that paddle wheel did followed this function, and we didn't know what the heat transfer was, rate of heat transfer. And so then you have one equation with 2 variables, and there's nothing you can do. But now we have one equation that'll have 1 variable, and we can solve for it. So the differential form of the first law says rate of change of internal energy, and we don't have any change in potential or kinetic, so I'll just write that as internal energy with respect to time is equal to Q dot, the rate of heat, the rate of energy added through heat, minus W dot. And if we, oh, and I didn't write some stuff down. It also says like this is 20 minutes, I believe. Does that sound right? Okay, so we know that all this happens over 20 minutes, which is 1200 seconds. And so if we integrate this form, we get the integral of du from 0 to 1200 is equal to the integral of q dot with respect to time from 0 to 1200 minus the integral of w dot from 0 to 1200 with respect to time. This integral is just going to be the change in internal energy. And so that we can just subtract. We have 1 kilogram, so you can forget about those kilograms there. And can someone subtract that for me? What's 276.67 minus 232.92? Okay, so 43.75, this is in kilojoules. And that's equal to the integral, so q dot is this function. So we have minus k over 60 times this integral from 0 to 1200 of t dt. And then I assume it's in kilowatts, but I don't have that written down. So right now, I'm setting everything up in kilowatts, and in kilojoules it'll come out to. And W dot is negative 0.1, double negative, so we have plus 0.1 integral from 0 to 1200 dt. So 43.75 is equal to negative k over 120 t squared. That's evaluated from 0 to 1200. So, and then plus 0.1 t from 0 to 1200. So we get 43.75 is equal to negative k over 120 times 1200 squared plus 120. So what's 1200 squared divided by 120? So 12,000 K is equal to 120 minus 43.75. What's that? 76.25? Yes! And so K is, I don't think I'm going to try this one. 0.006354. And I suppose we could figure out the units on that. Boy. Kilowatts per second squared, something like that. Okay, so the key to solving that problem was having the problem written down correctly. Q dot is in kilowatts, yeah. Oh yeah, so no squared. Here's the quiz that we don't have today. Okay, so now let's go through this quiz. This is the quiz I thought we had today. I'm actually pretty glad that I don't have to grade this. Okay, so the first question, did you get one of these, Jared? You want one? Did you get, Kyle, sorry. Did you get one of these? So the first one, for a simple compressible substance, how many properties are required to define the state? Yes. Yeah, that's a good strategy. Like, because, you know, like at always the easy questions the teacher asks are always first, you know? But no one really, like, you're not warmed up, so nobody really wants to talk. But if you just like yell out those first easy answers, they give you a pass on the hard ones then, and everyone else has to. So yeah, good strategy. What are the three important 2D projections of the PVT surface called? Okay, well, so there's only three combinations of two, but they have specific names. So the first one we talked about, phase diagram. Anybody remember what's on the y-axis and what's on the x-axis of the phase diagram? It's PT, yeah. And then, what's another one? Well, they just have a specific order of the two variables. That's all. PV and TV. It would look similar in either case, but it's lowercase. Would it look identical? I think it would look identical, just scaled, you know, by the mass. And TV diagram. Yeah. Three, what's the definition of quality? Yes. Yeah, very good. So quality, they call it X, is mass of the vapor over, you know, you can just think of it as the mass total. And this only makes sense for substances at the the saturation temperature between vapor and liquid. So, combinations of vapor, liquid at the saturation temperature and pressure. 4, what's the definition of enthalpy? We talked about it for specific enthalpy too, but this is the it can help you remember what it is. The main thing that'll help you remember what it is doing a bunch of problems that have enthalpy in it, and that's going to come up. But also remember that you can sort of loosely think of it as the internal energy of your system plus the work required to make space for it. So it's internal energy plus pressure times volume. Yeah, so if you think of something with a constant pressure, the work required to spread it out to a certain volume is the pressure times the volume, because the work done of expansion is the integral of P dV. And so that's like the work that it requires to go from 0 volume to the full volume, assuming that the pressure stays constant. Okay. Okay, what's the definition of the specific heat CV? Yeah, so that's the meaning of it, but there's a partial derivative meaning that if you had thought there was a quiz today, you'd have a good chance at this one, because right next to it in your notes it says quiz with an exclamation point, But so this one is the partial of the specific internal energy with respect to temperature, holding volume constant. And then number 6 asks about CP, the constant pressure specific heat. And that is the partial of the specific enthalpy with respect to temperature, holding pressure constant. The way I remember those is that you don't, I mentioned that this internal energy is strongly related to temperature, not strongly related to pressure. So you can sort of think of internal energy as being related to temperature but not pressure. So and so, whereas on the other hand, enthalpy has pressure in it, So that's how I remember pressure is the one that, C sub P is the one that has a pressure dependence. C sub V is the one that doesn't. Any questions about that? Okay.
Are we going to get like enthalpy and specific heat problems today?
I think what we're going to get, enthalpy is going to come up when we start talking about control volumes. And so, no, we're not really going to get any enthalpy problems yet. I just defined it. I defined it now because that's where it came up in the book. But it'll come up a lot later, but not now. We have a little bit left to talk about in what's chapter 3 in the book. We talked about ideal gases. We're going to talk about Now, just a lot of processes with ideal gases follow a certain relationship. They're called polytropic processes, and so we're going to talk about how to use that. And then we're moving on to our first time using control volumes. Okay, so yeah, polytropic processes. We've actually done problems related to this. So often during quasi-equilibrium processes, you have a relationship where the pressure times the volume with some exponent is equal to a constant. And most often, R is somewhere near 1, say 0.7 to 1.3 or something. And if the gas is also ideal, then the pressure times the specific volume is equal to RT. That's equivalent to thinking about it in another form, saying that the pressure times the true volume is equal to the number of moles times the molar universal gas constant times the temperature. So this is the one that's 8.314 joules per mole times Kelvin. This is the number of moles. And then you can combine these two relationships to, to eliminate variables. One more equation, you can eliminate one more variable. We've done problems where we've used polytropic processes with R equal to 1.2 or 1.3. So let me just do a couple of examples. First, I'm going to do one just we're going to assume that R is not equal to 1. And we have a polytropic process, so P times V to the R is a constant. And we want to derive an expression for the work of expansion. So that is the integral from state 1 to state 2 of P dV. Well, in order to do this integration, we have to express the pressure as a function of volume. So P, I'm going to call this constant C. So P is equal to C times V to the minus R. And then the integral from state 1 to state 2 of PDV, I can write as, I'll pull the C out. So we just have V to the minus R dV. And if we're integrating V to the minus R with respect to V, what do you get when you integrate this? That's right. So I'll write this as V to the 1 minus R over 1 minus R. And then we're evaluating, we still have the C, and we're evaluating from state 1 to state 2. And so now I can write this as C V2 to the 1 minus R minus C V1 to the 1 minus R all over 1 minus R. And notice that CV to the 1 minus R is equal to CV. Well, let me say it's equal to V times C times V to the minus R. And so CV to the minus R is P. So now I can make this substitution and just say this is equal to PV. And so the final answer is P2 V2 minus P1 V1 over 1 minus R. Okay, so for a polytropic process, you need to know the pressure and the volume at the end of the two states. But you don't need any other information about what's happening in between those two states. Well, I guess the fact that it's polytropic gives you, we filled in all the extra information based on the fact that we knew it was polytropic. So now, let's say that was part A. So now let's assume that it's an ideal gas. In this first case where we didn't assume it was an ideal gas, we got all this stuff in terms of two properties. Now we're going to add another relationship, which should allow us to eliminate one of these variables that we have in here. So it sort of makes sense that if we're going to use both of these, we should be able to represent that work of expansion in terms of a single variable. So now what we're going to do is calculate that same integral. We want to calculate the integral of PDV from state 1 to state 2, but we want the answer just in terms of temperature. In terms of temperature. Since it's an ideal gas, we have two forms we can work with. P times specific volume is equal to this material dependent R times temperature. Or that's also equivalent to the pressure times the true volume is equal to the number of moles times the universal gas constant, that's not material dependent, times the temperature. From part A, we know that PdV is equal to P2 V2 minus P1 V1 divided by 1 minus R. Now we also know that PV is equal to nRT, and since this is a fixed quantity of material, N is constant during this process. So P2 V2 minus P1 V1 over 1 minus R is equal to nRT2 minus nRT1 over 1 minus R, and you can write that as the number of moles times the universal gas constant divided by 1 minus the exponent times the difference of the final temperature minus the initial temperature. Yes, thank you. Any questions about that? So let's do one with numbers. So let's say we have 0.5 moles of an ideal gas. And it starts at 120 degrees Celsius. And then it's compressed in a polytropic process. And the relationship that we're going to have is P times volume to the 1.2 is equal to a constant C. Until the temperature reaches 200 degrees Celsius. What's the work W for this compression? Okay, first of all, do we expect this W to be positive or negative? Negative, it's compressed, so work's being done on the gas. So I guess I sort of pseudo went through this derivation again. This, I would recommend just trying, kind of remember these formulas. It's pretty easy to just go through the integration. I would just get used to doing it each time. So we know that W is equal to the integral of PdV from state 1 to state 2 We know that P in this case is equal to volume to the negative 1.2 times C. And so the integral from state 1 to state 2 of C volume to the negative 1.2 dV okay, because this relationship is P times V to the positive 1.2 is equal to a constant. So multiply both sides by V to the negative 1.2 to get P by itself to write as a function of V. So you get V to the negative 0.2 negative over 0.2. You still have the C in there. And that's evaluated from state 1 to state 2. What? Yeah, I guess I just won't give you that equation, so if you want to memorize it. So we have, we can think of this as C times volume 1 negative 0.2 divided by 0.2. I'll make that multiplied by 5. So 5C times volume 1 to the negative 0.2 minus volume 2 to the negative 0.2. And so now I guess I made that substitution that says V1 to the negative 0.2 is equal to P times V, because this is V1 to the negative 1.2 times V1. Nope, sorry about that. Let's get this C back in here. C, the 5's there. Well, I switched which one was. And so this is equal to this because now C times V1 to the negative 1.2 is equal to P. So now I can write this as 5 times P1 V1 minus P2 V2 instead of 2 minus 1. So up here after I did the integration, I had a negative coefficient. And so I wrote it as, instead of saying a negative bunch of stuff at state 2 minus a negative bunch of stuff at state 1, I said a positive, the double negative, positive stuff at state 1 minus stuff at state 2. So I got rid of the negative here by flipping the order of the subtraction. Okay, so now we know that P, V equals N, R bar, T. And so this gives us 5 times and the number of moles was 0.5. The universal gas constant is 8.314. The temperature at state 1 was 120 Celsius. And then P2V2 is equal to 0.5 times 8.314 times 200. And if you calculate that, you get negative 1,662.8 joules. Okay, so going through the math, you know, don't get hung up in the fumbly math or whatever. You know, this is all stuff you can think through yourself. Basic idea is, because we knew it was an ideal gas and because it was a polytropic process, we could figure out the work of expansion knowing only the temperatures at the 2 states. Okay. Yeah. Anybody have any questions about any of that? Yeah. Okay. Sure. So I did that integration to get rid of that negative sign here. I switched the order from, so I got rid of a negative and made it state 1 minus state 2. So we're here. And then you have to recognize that C times V to the negative 0.2 is equal to C times V to the negative 1.2 times V. Okay. The C times V to the negative 1.2 is P, and the other one is V. So we can replace this thing with PV. Okay.
Yeah, the 200s for the final temperature we just can't let them work.
The 200 was given in the problem. Yeah. So what's given in the problem is since we know it's an ideal gas and polytropic, all we need are the temperatures at the 2 endpoints, and those are given. Yep. Yes, that's right. Yep. I guess yes, exactly. V1 to V2. I kept writing it in terms of states because I didn't know when I was going to substitute stuff and whatever in it. And so if you're making substitutions here and there, you just have to remember that everything you substitute is at state 1 and state 2. So now once you've replaced this with P and you have this expression, so now this is the integral. Now you use the ideal gas law to replace PV with nRT. And then you just have numbers. Any other questions about that one? The definition is just that it's something that people just notice happens a lot, that often during a quasi-equilibrium process, not in fast processes, but in slow processes that are essentially in equilibrium at each point, you can often there's often an exponent so that the pressure times the volume to this exponent stays constant. In physics, I guess, I don't know which physics you talk about, like the ideal gas law. Do you do that at the end of physics 1 usually? But you might have, if you didn't run out of time at the end of physics 1, you might have done a lab where you actually had a little plunger and compressed gases and checked to see that it followed a polytropic process. It's kind of an experimental thing, like you just notice like, hey, this comes up a lot, and all we have to do is change the exponent. Now, we've been doing everything, so control volumes. Okay, so this is a new section. We've been doing everything by just watching a bunch of material as we do stuff to it. And we're following the exact same material. But there are a lot of cases where it's easier to keep your eye in one spot and see what's coming and going than it is to try to track a fixed set of material. You know, if you have any kind of, you know, if gas is passing through this device, it's pretty hard to keep track of where all your molecules are once they move past. And so these are useful when you're doing calculations involving turbines, pumps, valves, nozzles, diffusers. That's where I'll stop because I can't think of any more. Okay, but what all those things have in common is you're trying to analyze stuff that's happening while material's coming in one side and leaving the other side. And you're not, and keeping track of your 50 molecules or whatever would be difficult. So you'd rather pay attention to that volume. And so in this section, we're going to talk about two different balance laws. The first one is mass balance, conservation of mass. And then the second one is the energy balance. That's the first law of thermodynamics, but this time for control volume. And this is where, for the first time, you'll see why enthalpy is useful. So we're going to start out with the mass rate balance. And what it says is, if you're watching control volume, you're just looking at a certain space, the inside of a valve or something, then the rate of change of the mass in the control volume with respect to time is equal to the rate at which mass is entering at the inlet minus the rate at which mass is leaving at the exit. So again, we're using these two different ways of writing time derivatives to point out that they have slightly different interpretations. This is the rate of change of the mass in the control volume. This is the rate at which material, well, mass, enters at the inlet. And this is the rate at which mass leaves at the exit.
CV supposed to be like a subscript.
It's a subscript CV, just the mass in the control volume.
Okay.
And the rate at which mass moves through the inlet and the exit is calculated by the expression m dot is equal to the integral. Now, what we're thinking of the inlet and the exit as a plane. You're like if you're still on this side of the plane, you're in the control volume. If you pass that plane, you're out of the control volume. And so we're integrating over the area of that plane. Okay, so we're going to integrate all of this over the area that defines, like in Poltergeist, when they, you know, like when they're, like their leg goes into the portal and it's just gone, you know, it's just a plane like that. You're either in or you're out. And the area we're talking about is the plane of the area of the portal. It's a, yes, that's right, it is. And we're going to use a, yes. And what we're going to integrate over this area is the, so over this area, if you're trying to get the rate at which mass is going through this plane, you're going to multiply the, okay, so think about it like this. Mass is equal to the density times the volume, right? And you can rewrite that volume as the area times the, let's say, the length, right? If we're thinking of a material moving through this plane. And so m dot then is equal to rho times the area. Neither of those are changing in time. Times dl dt. And this you can just think of as the component of velocity is perpendicular to that area.
So the L from the first expression is the length of
So if this is, yeah, let me draw this. I think I can draw this. Okay, so here is the plane, okay? A is the area here. We're thinking of this material being extruded through okay? And so this would be L. So anyways, using this, the rate at which mass goes past this plane is equal to the density of the material times the normal component of the velocity. That's the part of the velocity that's perpendicular to that plane, integrated over the area. Now, question? Yeah.
What is V sub n denote?
V sub n is the component of velocity perpendicular to A, so it's the same as here. That means the same as that. Yeah, so that's not volume, that's a component of velocity. Okay, yes, everything's been volume. That's a component of velocity. Well, it's, yes, it is. So now remember, that density is just 1 over the specific volume. So you could also write this as the integral over the area of that normal component of the velocity divided by the specific volume, dA. Yeah, there's a little one and a big one. There's only 26 letters, so. It's the part that's, so if you have material, okay, so if you're trying to see how much stuff is going through the doorway, you know, and you have stuff going in every direction, okay? So say stuff's trying to go through this doorway. The only stuff that's going to make it through the doorway is the amount of stuff. So getting through the doorway is defined by having some part of your vector going perpendicular to the door. Okay. The total amount that gets through the door is just the total integral of all of the components that are perpendicular to this. The components that are going up, they bump into the door, or ones going back this way. You know, the only stuff going through the door are the components perpendicular. So that's what it is. But most of the time, we're not going to do this as an integral. This is what you'd have to do if there was some kind of complicated fluid mechanics you were dealing with, but we're not going to be dealing with that. Yeah. Mm-hmm. Yeah. Yeah, or like if you had to somehow like calculate what the flow was going to be based on fluid dynamics without just measuring it, then yeah, you'd have to use this complicated form. We'll use a simpler form. Good news. Simplifies if you know the average amount of flow in. Then you can just write this as m dot is equal to, so rho times A times the total speed. And this capital V is the speed, this average speed flowing in. And rho, again, is 1 over the specific volume, so you can write that as area times that average speed divided by the specific volume. And that's, you know, a lot easier to use. If the volume is in steady state, so steady state means that what you're looking at has no change over time in its properties. So no properties change, let's say in time. So the rate of change of mass in the control volume is equal to 0. And then the mass rate balance equation just says that the rate of mass coming in the inlet is equal to the rate of mass going out at the exit. So this one only holds in steady state, because obviously, like, you could have something with an inlet and an outlet and be forcing lots of gas in the inlet, and the mass inside is increasing, but only a little trickle of stuff coming out of the exit. Okay, so there's no reason in general that this equation holds, but as long as the amount of mass in the control volume isn't changing, this holds. Okay. Okay, let's do first a problem that relates to, so we're not going to be dealing with the phases of materials. We're just going to be dealing with basically an incompressible material. So let's say that we have, okay, so there's a pipe here dumping water into a barrel. So there's the level of the water. And down here, there's an outlet, and water's pouring out of this outlet. So this is a barrel filling with water. And let's say that the rate of water being added to the barrel, mi dot, is equal to 30 pounds per second. The density of the water is constant, 62.4 pounds per cubic foot. the cross-sectional area of this barrel is 3 square feet. And if it's just gravity that's causing water to come out of this exit, can you see how there would be a relationship between how fast water is leaving and how high this is here? The higher this is, the higher the pressure is here, and the faster water will come out. So the rate of mass leaving at the exit is 9L, where this is L. So we're going to find, no, that's L is the height in feet, and so the bigger L is, the higher the water is, the faster it comes out of the exit. So that's a variable, and we're going to find a differential equation for L using that mass balance.
Also, it's not, there's no time, like on the bottom of like 9L per second. How is it still a rate? It's just the distance.
Well, it's so yeah, there would be, so you know, when you have equations like engineering or science equations, you're dealing with that kind of stuff all the time. You know, like
Oh, yeah.
you know, like position is equal to time squared or whatever. It's the same thing as that. We're going to assume that if we put a value in for L in feet, the answer that comes out is in kilograms per second. In this case, I guess pound mass per second.
That's because the rate that it comes out
That's right. That's right. Because the pressure depends on the height of the water. All right, so we want to find this differential equation. And then we'll solve it. I'll show you how to solve it, but that's not something that that's sort of beyond the scope of this class. But it comes up with a form of differential equation that's pretty common in engineering and science. So knowing this trick will be useful for you. But okay, so first, is this steady state? Not steady state. So we're going to use the time derivative of the mass in the control volume is equal to m dot at the inlet minus m dot at the exit. So first, we know that mi dot, right, that's just equal to 30. And then me dot is equal to 9L. Okay, those are given. Now we have to figure out what we can say about, so what can we say about dm in the control volume dp? Well, we can come up with a relationship between the mass that's in the control volume and that L. So the mass is equal to the area times L, times the density, which is given. So that's 62.4 times the area was 3 times L, or 187.2 L. But we want the time derivative of this. So dm in the control volume dt, we're just going to take the time derivative of this. So it's going to be 187.2 times dl dt. And so the mass rate balance says 187.2 dl dt is equal to 30 minus 9L. And to get it in the form that you normally would see a differential equation in, we'll divide everything by 187.2 and get it all on one. No, I guess we'll get all of the expressions involving L on one side, and we'll get the other stuff on the other side. So dl dt plus 0.04808 L is equal to 0.1603. Who's taken or is taking differential equations right now? Okay, so how many boundary conditions do we need to solve this differential equation? Okay, well, what did you learn yesterday? No, okay, so okay, well, this is one, right? You can confirm that, and we just need one because we have one equation. It's not a system, and the highest derivative is first order. So we need one boundary condition, and our one boundary condition says that at time equals 0, L is equal to 0. So this is solvable, and I'll tell you the name of the type of differential equation this is, and then we'll stop for today and we'll finish it next time. But that's right. So this is a first order linear differential equation. That is made up of any equation that fits this form. So dx dt plus some function of t times x is equal to another function of t. Ours is even simpler. You know, they can get more complicated than this and still be called first order linear because we just have constant coefficients on these. These can be functions of time. So we could have made this all uglier and still solved it with the same approach. But whenever you have, okay, and what makes it linear? So why is this called linear if you have this multiplied by functions and stuff? You don't really think of that as linear. But one independent variable is what makes it an ordinary differential equation. What makes it linear is that we don't have any, so the expressions involving the derivatives of our dependent variable x, so the first derivative and the linear term, those aren't multiplied by each other, and they're not squared or anything like that. Okay, so we just have something multiplied by the derivative, something multiplied just by the dependent variable. And if you can write your differential equation in this form, there's a closed form solution for it. Okay, so next time I'll show you how to solve this, although that it's not something I'm going to give you problems on in this class or anything. It won't take super long. And then this is one where all we have is liquid coming in, liquid inside, liquid leaving. But after that, we'll go into cases where you might have a vapor coming in, you might have saturated combination of states inside, and then a liquid coming out or something like that. And then we have to combine some of the other stuff we've done with this approach. Okay. Have a good weekend. Oh, don't forget to leave your binders if you haven't yet. And if you don't have it with you, I'll take them tomorrow too.
I will still stop by.
Okay, great. Perfect.
Hopefully we'll have more time.
Yes, hopefully. Okay, see you then.
Have a good weekend.
You too.
Yeah, it's like a quiz we're gonna